All right, so you can see on the announcements, the last homework assignment for chapter 12 is due on Sunday. That covers activation energy and mechanisms. It's mostly on mechanisms. There's just a tiny bit on activation energy. I will warn you, there is one question where there is a temperature in Celsius that is in the hundreds. It's like 700 something. Whenever the temperatures are that high, people forget to turn to Kelvin, but you have to turn the temperature to Kelvin, even if it's in the 700s. Okay, so remember with a mechanism, what we're doing is we're showing the steps of the reaction. And in those steps, we wanted to, or the elementary steps show the molecules that are actually running into each other. So by step one, saying H2O2 plus Br minus, what we're saying is that Br minus collides with H2O2. So we can say that that step is second order, because in order for those things to collide, you have to have the H2O2 and you have to have the Br. If you don't have those things, then, or if you don't have enough of them, then the reaction slows down. So from the mechanism, we can tell how many elementary steps there are. And we can also tell which one is rate determining. How do we know which one's rate determining? The slope, right? So the fastest one's great. They're gonna speed up the end of it, but that first step being slow is just gonna keep us slow unless we can speed it up somehow. If we are looking at this one, what are the intermediates in this? Remember, 8 intermediates will appear first as products, but don't appear in the overall reaction. So look at the chemicals that are on the product side and see which ones don't appear in the overall reaction. The hydroxide, yeah. And so this one's a little bit tricky because we have a 2 hydroxide here, but on the other side, there's only 1 here, but it's in 2 different steps. So being in 2 different steps, they do end up canceling out overall. So hydroxide is 1, and there's another one, HOBr, and that is our hypobromous acid. Think about how to say that. Okay, so if we were going to write the rate law from this, what we would do is we would take the slow step, take the reactants only, and we would write a rate law. Rate laws always have K in them. So the first thing we put is K. And then we would put the reactants in brackets. Okay. If there are coefficients to those, then those coefficients would become exponents here. So our reactants here are H2O2 and Br minus. So according to this mechanism, that is what the rate law should be for this overall reaction. So if the first step is the slow step, this isn't too difficult. It does become more difficult if the second or third step is the slow step, because then you might have an intermediate in there, and you don't want an intermediate in your rate law because you can't like control that from the outset, knowing that there's going to be more or less of that. All right, anybody still need this slide? We said that this was a 3-step mechanism. So we can turn that into an energy diagram. How would we show there being 3 steps in the energy diagram? How do we count the steps? The hills, exactly. So we're going to have 3 hills, and we want to show the first step as being the slow step, so it has to have the highest activation energy. So I'm going to show you this image. It's 3 steps. Remember that our activation energy isn't determined by how tall the hill is overall, but how tall it is compared to the last valley. So in this one, step 1 and step 2 look like they're pretty similar in activation energy because of that coming from just the previous thing there. So we kind of have to measure it out. This was a diagram I had separate from that particular mechanism, but it came close. Now, if this were the overall energy diagram, would this be an endothermic or an exothermic reaction? Is it overall downhill or overall up? Do you end up lower in energy or do you end up higher in energy? Lower in energy. So overall, we ended up downhill. Downhill is exothermic. Okay, so let's do another mechanism example. This is our overall reaction. And we know the rate is K times NO squared times O2. So we might say, well, maybe this just happens in one step. That's always a possibility. So one thing we should check is, since if we're saying it's one step, it has to match because there's just one step. So that's the first thing we check. The next thing that we can look at is, does the rate law, which we know is true from the bottom, that's the true rate law, does that match what we would get if this were the only step? So if this is an elementary step and we were going to write the rate law, we would write K times the reactants raised to the exponent of their coefficients. So does that match? Yeah, because we would write nitrogen monoxide squared, because there's a 2 by the nitrogen monoxide, and then we would write concentration of oxygen. Okay, so that matches, but there's a third thing we have to check, and this one is just a matter of it being reasonable, not whether or not it's possible. So this is a possible mechanism, but somebody might say, I think there might be a better way to do this, because what's wrong with this? What would have to happen all at the same time? You'd have to get all 3 of those molecules to collide all at that same instant in order for this mechanism to be the one that works. And that's unlikely. So we would say this is termolecular, and termolecular steps are very, very large. So that seems unlikely. Okay, so here's a second possible mechanism. This one is 2 steps. Are all the steps either unimolecular or bimolecular? That was our problem with the last one, was we added termolecular. So that one is bimolecular, which is fine. What about the second step? Also bimolecular. Okay, so that's reasonable. The second thing we want to check is, if we add this up, are we going to get the overall reaction? So the same thing that's at the very top of the screen. And so the only intermediate we have is the N2O2. Those would cancel out, and we would end up with 2NO plus oxygen as our reactants, which matches. And we'd end up with 2 nitrogen dioxide as products, which match. Okay, so that works. So the last thing that we're going to check now is, does that rate law match? Now, which step is rate determined? The second step is rate determined because it's the slow one, right? But we've got an intermediate in there. So we're going to have to do a little bit of algebra, but it's chemical algebra. So we're going to treat each of those chemical formulas, especially the intermediate, as like a variable like X that we can just kind of move around. And so that whole thing's just going to stay together as X. So let's see how that works. Initially, we'd say that for the rate determining step, the rate law would be K times N2O2 times O2. But we don't want to have the concentration of N2O2 in there. So we're going to look at the step before that and see if we can put that intermediate as a product as part of a rate law. So that is an equilibrium. Equilibrium means the reaction goes in both directions. So I have a rate going forward and a rate going reverse. And because it's equilibrium, those rates are equal. So I can write my forward rate law as K times NO squared. And I can write my reverse rate law as K times N2O2. So are all of these K's the same K? No. So we're going to put labels on them. So we're going to have a K2 for the second step, and then we'll have a K1 forward and a K1 reverse, or sometimes we write K negative. So the rate forward and the rate reverse are equal to one another, and that's because it's at equilibrium. And how do we know it's at equilibrium? The double arrows. The double arrows tells us it's at equilibrium. So that's why we can say rate 1 is equal to rate 2. So this means that K1 times the concentration of NO squared is equal to K negative 1, which just means the reverse reaction, times the concentration of N2O2. So now we have 2 equations that have this concentration of N2O2. So what I'm going to do is I'm going to rearrange this thing at the bottom so I get N2O2 by itself, and then plug that into my top equation. So you might remember from algebra when you had to solve 2 equations, sometimes you would solve for X and you'd have something that had Y in it, and then you would plug that back into your to the other equation in order to figure out what the numbers were. Okay, so let's see what that looks like. Okay, so this so far is just what we had at the bottom of the screen. There's nothing new here. So when I rearrange to solve for the concentration of N2O2, all I've done is I've divided by K to the -1. That makes sense? Just move the K to the -1 to the bottom. All right, so now I'm going to take that whole thing and I'm going to plug it into this up here. So I'm going to rewrite K2 is going to stay the same. O2 is going to stay the same, but instead of writing this, the N2O2, I'm going to write this, the K1 times NO squared divided by K -1. Right, so plugging into the red equation there, this is what I get. All right, so that looks all very messy because I got all these K's all over the place, but they are all constants of some kind. So if I had the numbers 2 and 7 and 4, and I plugged those in there, it would just be another number, right? Okay, so I'm just going to group all of those labeled K's into K overall, okay? So the rate is K overall times NO squared. Now, does this match the rate law that we saw originally? It's not on this screen anymore, but if you go back in your notes, the original one. Okay, so this is kind of a challenge way to do this. What I would do on your test is if I offered you one where you had to solve for the rate law this way, that would be bonus points. Okay, so if you can do it from the first step, I would expect that. All right, and so here's another one that would be difficult. We're not going to walk through this one. Okay, so first of all, looking at this graph, what kind of information could we get from this graph? In order to answer that, before you jump to any conclusions, look at your axes. Make sure you know what we're showing in this. So what is this on the bottom axis here? What does that T stand for? Temperature. The capital T is usually temperature. Temperature makes me think of thermo. Thermo is energy. So what can I tell from this? Or what information could I get by doing so? Can I tell the order from this? Not from a temperature graph. This is the one where I can get the activation energy. So this is similar to the last question on your quiz. So we would look at the slope. Now, be careful when you're looking at this because it's written in reverse with X at the end. So we're looking at the 2372. That 2372, is that equal to the activation energy? No, because remember the slope on this one was EA over R with a negative in front of it. So we would have to multiply that number by R and drop the negative, and that would be how we would get the activation energy. So first order reaction is carried out at several different temperatures. The data are plotted as natural log of K versus 1 over T. That's exactly what we saw on the previous thing. How is the slope of the graph related to EA? So what, if you have the slope, say in the last one was 2300, what calculation would you have to do? So take a look at all of those. Which one do you think it is? Okay. Getting both A's and B's on this one. And they're very similar to each other, but there's a negative sign. So let's go back and look at our graph. Is the slope negative or positive? The slope is negative. Can activation energy be negative? No. Activation energy is up, so it is positive. Okay. So in order to get rid of that negative, it has to be B, right? You have to take the negative of the negative to get the positive. Okay. From this diagram, I can tell lots of different things. What is, or how many steps do we have here? 3 steps. What is one of the intermediates? N2O2, it first appears here. Now this H2 is just kind of a holdover reactant, but this is an intermediate that appears. And then we get an N2O, but that's not our final product. So that's going to be another. So we can see the intermediates and notice how they're in the valleys. Okay, intermediates appear in the valleys. At the tops of the hill, we have A, B, and C. What kinds of particles will we find there? What do we call those? What are they? Not catalysts. think about as you're going from one thing to another, you are transition states. You're transitioning from one thing to another. So that's a transition state. Sometimes you hear activated transition state. Okay. So A, B, and C are where we put stars. Those are transition states. D and E are intermediates. Did we say how many steps this was? 3 steps. And is this endothermic or exothermic? Exothermic, because the products are lower in energy than the reactants. All right. This diagram is just to kind of give you an idea of overall what the energy diagram would look like. But the question is taken from an ACS exam. So it says the reaction of A plus B going to AB. So A and B would be on the left-hand side over here. And then the product AB would be over here on the right-hand side. It says that reaction has an enthalpy of reaction. What letter do we use for enthalpy? H. So the enthalpy of reaction is negative 85. And so that's why we have a downhill reaction, because it's negative. If the activation enthalpy or activation energy for the forward reaction is 120 kilojoules per mole. Okay, so the top vertical line, that's 120. The bottom one is 85. What is the activation energy for the reverse reaction? So this would be going from here to the top of the hill. So what do we have to do with those two numbers? We have to add them together, but remember that because that 85 is a negative, we want to make it positive because we're going to go in the reverse. So we're reversing that one. So it would be 85 plus 120, which should give you D on this one. Okay, that makes sense? All right, so that's the kind of question where you have to put several ideas together. So a lot of times for your quizzes, I try to keep it simple where it's just, okay, we're drawing one piece of information. But remember, at the end of the semester, you have this ACS exam, and sometimes they'll ask you to put together the idea of what is the enthalpy and how do you read that on a graph, or what is the enthalpy and the activation energy? What happens in reverse? That's what we're doing here. Okay. A catalyst, going back to what somebody said before, a catalyst is added to this system represented by this energy diagram. Which dimensions in the diagram are changed? So we're going to have changes in size of possibly number 1, possibly number 2, possibly number 3. So when we looked at the catalyst, sometimes it's 2 steps. How is the hill for the catalyst different from this hill? It's going to be short, right? And so what it does is it lowers the activation energy. So which of those numbers is measuring the activation energy? 1 is measuring the activation energy. So 1 is definitely going to change. So it's not going to be C. So then we have to ask ourselves, do the other things change? So this is why I pointed out on that diagram that the reactants and products stay in the same place. Those are the same things. They're fixed by, the laws of nature or whatever. Adding a catalyst doesn't change where those are. So we're basically going to draw a hill underneath that hill, but it's going to have starting and ending points the same. So will 2 change? No, 2 won't change. That's our enthalpy of the reaction, right? What about 3? If the hill is lower, does 3 change? Yeah. So our answer then is going to be B, 1 and 3 only. Okay, now some mechanism practice. This one is written on the paper, so you don't have to write out the whole thing. So we have a reaction here. The tricky part about looking at mechanisms when they're actual chemicals is that you have all the same letters because the elements are the same, whereas if you have A's and B's, like, things look very different. So it makes it a little bit harder when you put the chemicals in there. So notice the subtle difference between, we have C3H7I and C3H7 plus. And then we also have at the end C3H7Cl. All right, so pay attention to the details and how that changes. Okay, so we think it might be happening through this mechanism. So in order to answer the question, what is the rate law? What do we first have to figure out? Rate law comes from what step? Rate determining step, and the rate determining step is the slow one. Okay, so this is a two-part question. First, we find which is the rate determining step, which is step one, because it's slow. Then we come up with the rate law. So rate law is going to be K times the concentration of just the reactant there. So C3H7I. Okay, how many intermediates are there? All right, so we have one intermediate, it's the C3H7 plus. So this is a particular kind of organic reaction, and I believe this is a next one. This one, we're going to have two different mechanisms, and we're going to compare it. Okay, so your first, the reaction there is going to be the same for them, but then we're going to compare the two mechanisms. So we have NO2 plus carbon monoxide forms nitrogen monoxide and carbon dioxide. And then the temperature that it happens at is not important to us because we're not changing the temperature. So we're going to ignore where it says temperature. And we have a rate law, K times NO2 squared. Okay, so mechanism one. Does this mechanism match the overall reaction? So this is where we have to add everything together and make sure it matches the thing that's at the top. Oh, I didn't advance this. I'm sorry. There you go. So our NO3s are going to cancel out. That's an intermediate. We have an NO as a product here, and then as a product there. We have a CO2 as a product here, and as a product here. And we have let's see, we have two NO2s here, but only one up there. Is that a problem? Or do we cancel out one of the NO2s? Yeah, because the second step has that as a product there. Okay, so it does match the overall reaction. Now let's check molecularity. Remember, we're looking to see if any of them have 3 molecules or more. Do any of them have 3 molecules or more as reactants? No. Step 1 is bimolecular. Step 2 is bimolecular. Now with step 1, we might see that sometimes written as 2 NO2, but they're both bimolecular. Okay, so molecularity is okay. And then what is the rate determining step? So in this case, it's going to be what, first or second? First, because that's the slow step. All right, so then how would we write the rate law for that? Rate law always starts with K, and then concentration of NO2, and is it going to have an exponent? So the way this is written, it kind of looks like we would write K times NO2 times NO2, right? But if we were writing K times X, can I combine those X's? Yeah, and that would be X squared. So this K times NO2 really is K times NO2 squared. So now I have to go back to the original question, the text of the original question. Is that the rate law we were hoping to find? Yeah, okay, so this is probably the good one, okay? So it does match the rate law. All right, now here's mechanism 2. So the screen actually did change. So here we have a very similar step, but it is saying that that first step has a very fast equilibrium, and which step is the rate determining? Second step is rate determining, okay? So this is where we have to do a little finagling and see if we can come up with the correct mechanism. All right. The molecularity, are we still looking at unimolecular, bimolecular for both steps? Yeah, they're both bimolecular, so we're good. We said the rate determining step was the second step and doesn't match the rate laws. This is where we got to do our algebra stuff. All right. So the rate law from this would be looking at that second step. carbon monoxide, which is a reactant, so that's fine, times the concentration of NO3. Okay, but maybe we can get rid of these things and replace it with the other stuff. Let's see what happens. All right, so can we substitute for NO3? What we're going to have to do is go back to the first step and write the forward and reverse rate laws as being equal to one another. So the F that I have here is the same thing as the 1 that I had on the other PowerPoint, and the R is for reverse, so that's the same as the -1. And we're trying to replace NO3, right? We don't want NO3 as part of this. So to solve for NO3, just like I did the last time, I'm going to put the forward rate law on top, and then the chemical that I don't want, we didn't have last time another chemical. This time we have another chemical, the NO2, and we're dividing by K reverse. So I've combined K forward and K reverse into just K. That's a K overall. And remember, the whole reason for solving for this is we wanted to plug that in to the NO3, right? We wanted to have that so we could get rid of that intermediate. We don't want the intermediate to be part of what's going on. So we plug this in. So at this point, we have a rate law that does have NO2 squared. So that matches. But we have two problems. We have carbon monoxide is still in there, and that's a reactant. We said that wasn't something that depended upon it. And we still have another intermediate. And without more steps to do canceling, it's really going to be kind of hard to get rid of that intermediate within the rate law. So does that work? Not so much. We thought that the first rate law was going to be better, or the first mechanism was going to be better, and it was. Okay, so one last question here for review. The normal boiling point and vapor pressure at 25 degrees Celsius are measured for liquids in two flasks. Flask A contains pure water. Flask B contains a 1 molar aqueous sodium chloride solution. Which flask contains the liquid with the higher boiling point, and which flask has the higher vapor pressure? So now we're going back to chapter 13. So we have to ask ourselves, when I dissolve anything at all in a solvent, what happens to the boiling point? What happens to the vapor pressure? Okay, so we call it the colligative property boiling point what? Elevation. So boiling point is going to go up. So which of the two should have the higher boiling point? B, because it has the sodium chloride. Pure water should be low, so it should be one of these two. Okay. Now the reason the boiling point goes up has to do with the vapor pressure. So at the surface of the molecules, or at the surface of the liquids, in the pure water one, there's water to evaporate. In the concentrated sodium chloride, there's water, but there's also sodium chloride that's kind of keeping that water from evaporating. So which one's going to have the higher vapor? A will have the higher vapor pressure, so C is our correct answer.